Hello, so today we're gonna see some new things about MIDI. We're gonna see the functions get and set all from Reaper API. So if you go here in the famous website, you look for get MIDI all events. You have a get all events, you have also a set all events. So basically what these functions came first from the newer API, which are things like insert note or set media or set CC, set event, set note. All these functions came later. Before we had only get all and set all events. The reason that we still use it is because they are much faster than the other API, the newer. And the reason for that is that you're gonna just make two calls from the Reaper API. So first you're gonna get all events, and this will return a string with all information you need. Then you're gonna manipulate this string, and then later you will insert the new string as the new MIDI. And then all functions are basically Lua and not getting things from Reaper itself. So this will make your functions much faster. So consider using get all or set all if first you are doing a project that really needs speed. For example, you are doing a script that sets everything at each frame. For example, here the multi-tool script, a famous script from Julian Sanders, one of the best scripters in MIDI in Reaper. Sorry, let me correct overlapping notes. Okay, now I can run multi-tool. Multi-tool works really fast. Here I have an item with 10,000 notes, and it really works, and it needs to manipulate the MIDI each frame. It's a little laggy, but it's really fine. And considering I am doing this with 10,000 notes, are more than fine. If you were to use the newer API, it wouldn't be as fast. It just wouldn't. So consider this get and set all functions if you really need speed. You also will need to be kind of adventurer because the functions will be much more complicated to use. Let me give you an example here. So here I made two functions. These functions just randomize the position of the selected note. I will put on the description out of this code. And this is quite a long script. Up here, it is folded. Let me unfold. Up here I have many functions that I will be using today. I won't get in everything and explain how they work, but you can figure it out. I will explain the concepts though. So if you down here after the functions you have a how to section, and here I have some examples that you can study. For example, a basic loop that we're gonna see, basic loop using iterators. Here another example to delete CC and add CC. And here the two functions I'm gonna show now, randomize notes using get and set all API, which is the fastest API. And you can see it's quite a long code. It's like almost 100 lines of code for this simple task of randomizing the note's position. And using the new API, which you probably can read this code and understand everything, like you're gonna get all takes using an iterator, you're gonna disable sorting, count the events, loop for every note, get a random value, get information about the note, get the note position. Then here you are adding the note position in seconds with the random, which were in milliseconds, but now it goes to seconds and then convert into PPQ. And if you don't know PPQ, watch back later or my previous video about MIDI, which are pulses per quarter notes and everything you need to set in pulses per quarter notes. Converting back into PPQ and finding the end position of each note, which needs to randomize by the same amount, and then setting the note again and sorting the take. So I am calling these two functions, and it will print here how much each of them took to run. So let's first start with one MIDI item that has, let me open the inspector, 1000 notes. Okay, so I'm gonna select everything here, 1000. I will run the function, and it's on the other screen. Here you can see how much time it took. Wait a minute. Here. Okay, so the get and set all events took 0.00 how much zeros? 2 zeros and 7 seconds, so really fast. And the newer API, which is slower but easier to use, took 0.05 seconds, so it's already a lot more, but it's okay. For this function doesn't matter. But now let's select 10 items of 1000 each, and let's select All MIDI. Let's run it. So the get and set all took 0.07. It basically took 10 times more, and here it also took 10 times more to run for each of these items. So okay, it is linearly that they are getting slower. But now, instead of 1000, let's take 1 of 10,000, which are basically these 10 glued. Okay, let me do here with this one. So I just glued those items, and I'm gonna run the function again, and it will take some time. Oh, it ran it. So with 10,000, the get and set all still took 0.07, so it didn't make much difference. But the new API, look how slower it was. It took 5 seconds, 5.1 seconds. So much slower. So the new API, the get note, set CC, delete note, etc., took much time when you are working with MIDI items that have a lot of notes, like 10,000 or more. So consider when you are working in a script, if your script you need to work with a lot of notes, or it needs to run on a different script, if you need to use the get all, or you can use the newer API, which will be slower, but it doesn't matter on the end. Okay, so now let's start to view how to use the get all and set all. Okay, so to start talking about the get all and set all, we need to talk a little about MIDI protocol, and you need to understand a little more of the basics of it. And we need to know how the bytes work, what is a stats byte, a data byte. Maybe you already know it, so you can jump ahead on the video. But for the others that don't know, we will try to explain the basics of it. If you want to know more or see a complementary video, look for this channel, Simon Hutchinson, and look for the video, The MIDI Protocol, MIDI Messages by Simon Hutchinson. And it's a really great video. It explains really well and really fast how MIDI works, and And I really like this part of the video. I actually will use a screenshot of this image, because here you see many good information. Anyway, so MIDI are basically bytes. So bytes is a conjunct of 8 bits, which are zeros and ones. So a byte can be 0, 1, 0, 1, 0, 1, 0, 0, 0, for example. It's 8 numbers which can be 1 or 0. Okay, so the MIDI will always, a MIDI message will always start with a status byte, and then it will have data bytes before after it. Some MIDI messages just have the stats byte, but most will have this combination, stats byte and data bytes. So think of it just like a train. You have the head of it, which is the status byte, and you have the wagons, which are just following the status byte with more information. So the head, the main function of the head is to say which type of MIDI it is, and for which channel, if it is a message that have a channel. Okay, system messages in MIDI don't have channels, but like notes have channels, control changes have channels, pitch have channels. Okay, so the head will have this so the head will have this function of telling which type of MIDI it is and the channel. And data bytes will just have complementary informations. So a status byte always starts with a 1. It's how you recognize, oh, this is a status byte, because it starts with a 1. A data byte starts with a 0. That is why it is recognized as a data byte, because it starts with 0. So this is why you have 128 possibilities, because the first byte is already used. So the status byte, as it starts with 1, the first 3 bits are used for determining the type. So you have here 2 on the 3 options of types, that equals to 8 types. And the following 4 bits are used to determining the channel, or on the cases of system messages, it determines the type of message. So for now we are not going to talk about system messages. So these 4 bits will, for us, for now, we'll talk about channels. Okay, let's continue. So yeah, we have 8 types and 16 possibilities of channels, because 2 on the 3 equals to 8, 2 on the 4 equals to 16. And here is a really good resume that we have on the other video that show us which combinations of bits equals to each type of message. For example, note off starts with a 1 because it's a stats byte and have 0, 0, 0, 0. Okay, so this is the note off. And the number 1000 in bits, in binary, so 1000 equals to 8. This is for why in my code and how I use get and set all, I refer to the notes off as type 8. Note on will start with 1001. And this number as in binary is equals to 9. And if you follow the list, it is in order. So 8, 9, 10, 11, 12, 13, 14, 15. Yeah. And that's why in my code I will address note tone as notes type 9. Okay. So there is just one detail that we must talk about that note on MIDI MIDI messages that have the note on but have velocity equals to 0, they will be recognized as note off. So note off, you have two options. So, or they are from the note off types, or they are note on types with 0 velocity. Okay, so let me erase this. Okay, so here I have some examples for us to study. So 1001. This equals to the number 9. So if you will see here, it's a note on. And 0000 equals to channel 1, okay? Because it's the first option we have. We could also say channel 0, but normally in MIDI we start with channel 1 and not channel 0. So it's 1 based. And following this status byte, we have other 2 data bytes. Okay, oh, sorry. Here should be 0. If it started with 1, it would actually be a status byte of a system 6 message, but it starts with a 0, it's a data byte. So it's a note on, and following it we have 2 data bytes. The first data byte of a note on say which note it is. So for example here, this number in binary could be read using hex numbers. We could read as 3C and is equals to 60 in decimals. So this is equal to note C4. Okay, hex numbers are really great for us to see a stats byte at least, because we can see 1001 and 000. They always will be divided in 2 algorithms in hex numbers, so we can see the type and the channel using hex numbers. Okay, I don't use it a lot for recognizing data bytes, but for status bytes it's really good. So here is the note. It's a note 60, and this equals to FF, that equals to 127. So it's a MIDI note tone of the note C4 with the maximum velocity. And here we have 11000, 1000, which equals to 8. So it's a note of channel 1. And same thing, so from the note C4, and the next data byte is 00. So note of velocity is equal to 0. It could be like 10, that would be like 2. Okay, so it would have velocity. Note offs can have velocity too. Here, we have a note on type of channel 1 and of note C4 again. But now we have velocity equal to 0. So this is also a note off. So here we have the number 1011, and this in hex equals to B. B in hex is 11. Basically, you can count. So 9, 10 is equal to A in hex, and 11 is B in hexadecimals. And the type 11 is a CC, a control change message, and it is 001, so it's channel 2, and the data bytes, the first one tell which control change it is, so it's the number 7, it's CC7, normally used for volume, and here is the value of it, so 60, it's on the middle. Okay, so these are stats bytes and data bytes about MIDI. Okay, so we saw a lot of things about MIDI. Let's see now it on Reaper. For example, go to your create a new MIDI item, go to the piano roll and view, click raw MIDI data. This will show this window that will show all of the MIDI data that we have. So for example, if I add a CC here on the middle of the item, you can see it added on the list. So you can see from here is the first byte, the second byte, and the third byte. Here we have actually 2 CCs. You can see it's the CC because it starts with 11 or B. And here you have informations about the position they are in PPQs. And all items, even if you start with a really blank item like this one, will always have a B0, a CC on the channel 1. And this CC is, let's see, the second data byte. I know it's 1, 2, 3, but let's go to a converter. So hex to decimal. You can see it's 1, 2, 3. So CC 1, 2, 3 for Reaper represents the end of a MIDI item. If you change the end of it, for example, you make it larger, you can see this number changes. So as I shrink it, these numbers also shrink. So Reaper has this hidden CC 1, 2, 3 at the end of a MIDI item. You can't even try to access it over CC 120. You can't access inside Reaper. Okay, so CC 1, 2, 3 are for closing MIDI items, and you can see it here. Here, these 2 numbers, the first one is the offset from the last message. For example, if I add another CC here and put this really close to the start, and this also too, so you can see this is the offset from the start of the item, and this is the offset from the previous message. So the first number is always from the previous message. The second is their place on the item. So it's the PPQ. The first message will always equal both, but the second one you could reach it by adding all the values. So this is the position it is from inside the item. Okay, so this is the raw MIDI data window that you can use to guide your studies of MIDI inside Reaper. Now let's think. Okay, MIDI is made of the following of many bytes. How we can put this thing on a string? So a string is also a sequence of bytes. Each character, it's a byte. For example, if I go here and create a string and put, I don't know, A less 8, put these 5 characters. It says it has 5 bytes. And what Reaper does with the get all and set all functions is put each MIDI message in a string byte, and you can use these strings to convert to numbers if you want and modify the message if you need. I also have in this file that I passed you. You can go to here on this section, spec, unpack, MIDI, and flags functions. You have things like unpack MIDI message, where you will pass the MIDI message as a string, and it will return the message type. So for example, if a note tone, it will be the 9, the message channel, the value 1, which is the first data byte, the second data byte, and text for MIDI messages that have text. And here is a table it returns with all bytes inside the table. You also have pack MIDI messages for making new MIDI messages and converting them to strings, where you can pass the MIDI type, the MIDI channel, and all of the data bytes. You can put each one as an argument, or if a text, you could also put the text itself as one string. And so these 2 functions are really great for unpacking MIDI from strings to numbers and numbers to strings. And now that we understood okay, so in Reaper, as we saw, each character will be a byte. But for each MIDI message, not only we need the MIDI bytes, we also need the bytes for their position. Because if we just had like, oh, now we have a note, now we have a CC, now we had a note off, we wouldn't know where they are in their position if the note is selected, and the tension of the curves of the CC. All of these also needs to be on their own bytes. And you can go, here I made a table to resume it. So the string that returns from the MIDI get all events will have this structure. The first 4 bytes will be about the offset. So if you take these 4 bytes and put them together, they will return an integer, which is the PPQ from the last message. This gives you the possibilities of, let me put some comments here. So 4,294,967,296 PPQs. So it's a lot of PPQs you have that you can have between 2 messages. I calculated it's like 1 millionth bar of 4. Let me get the number exactly. So it's this number that we have in PPQs that we can have between 2 messages. And if we divide this between 960, this gives the amount of bits we can have. And if we divide it by 4, these have the numbers of bars of 4. So we have 1,180,481 bars of 4 we can have in between 2 messages. And Reaper have some tricks to have messages that are further from that apart. Okay, so the first 4 bytes or the first 4 characters of these strings that returns from the MIDI get all events will return an integer. And the second thing, the 5th byte, so here the first 4, and the next byte will return a flag, which is just 1 byte. And this byte shows if the note the MIDI is selected, if it is muted, and if it's a CC, it can also say if it's their curve type. So the last bit is if it is selected, the not last bit is if the note is muted, and the first 4 tell the curve type of the CC. So here are the possibilities. And the next 4, after these 5 bytes, we have more 4 bytes that says how long is the MIDI message. Because MIDI messages can have, for example, 3 bytes, for example, no tone, the status byte, the data byte 1, data byte 2. But for things like program change, you have 2 data bytes, so data byte 1, status bytes and data byte. So you have 2 bytes. So this message length is just to tell us how long is this other thing, which is the MIDI itself, the MIDI bytes. So for example, a no tone, you will have 12 bytes. So 4 of the offset, 1 of the flags, more 4 of the message length, which is already 9. And this for a no tone, you have the status byte, you have the data byte 1, which is the note, and you have data byte 2, which is the velocity, so 12. And this is how you use the string that comes out of the get all. So let me go here on the file that I passed you and go to here, basic loop, the function basic loop, how to make a basic loop using get all events. So here first it is using a iterator just to go to every take that is open on the MIDI editor. So on this first take it gets the take and return the MIDI as a string. First thing it does is getting the string length and where it says where it will start reading it. So we're gonna start reading on the first byte, of course. And the PPQ, this is just for counting where is each message. So we say 0 because we just started reading. And then we're gonna iterate this string until the place where we are starting reading this string is lesser than the length itself. So when we read all of the characters, it will stop reading. Okay, so we're gonna update this every loop to say which position we are reading the string. It is updating here actually. So we're gonna use the string unpack function to unpack the MIDI string. And this first string here is the thing that you must use. I4, B, S4. You need to use this. I4 is corresponding of the offset that I talked. It have 4 bytes. So we want an integer using 4 bytes. Okay, so it's gonna go to this string, gonna get 4 bytes and convert them to an integer. Then it will pick the next byte, which is an unassigned byte, and convert it to also an integer. Okay, this will return flags. The I4 will return offset, the B will return flags, and S4 it is basically means that we're gonna get the next 4 bytes as a number and then use this number to get the number of bytes that we need and return it as a message. So as a string, message will be a string also. S actually means string. So we get the next 4 bytes, which if you go here, corresponds to the message len, and this return a number of how long is the MIDI bytes. And then it will read this and return as a message. Message is just these bytes and that it got. And here is the string position that is stopped reading on the MIDI string, okay, that we're gonna use to update where we are reading. Okay, this can be confusing, I know, but if you go and try to understand here by the rhythm, this structure, you can see how this makes sense. The I4 gets the first 4 bytes for the integer, B is the unassigned byte for the flags, S4 is a string preceded by its length in this case 4 bytes, so it will return the MIDI message as a string, because it will read, oh, this is 10 bytes, so you get 10 bytes and return these 10 bytes. Okay, so inside, after doing this, we can update the position that we're gonna read on the next loop, and then we can also update our offset count, because now that we have the offset that this mid message is from the previous message, we can say offset plus offset count that were 0 equals to offset count. So we are just adding to our counting. So this return the PPQ position of this MIDI message. And now we can use my function that I talked earlier, unpack MIDI message, and pass to it the message itself. And it will return the type, the channel, the value 1, the value 2, and text and message as a table. Okay, so this is how you make a basic loop inside using get all. But there is an easier way, which is making an iteration function. Okay, so here same thing. Get the MIDI editor, get the iterate each take inside it, get all events of this take in a MIDI string, and here I made a function called iterate all MIDI. So if you go here on the code, it's on top. You can see and try to understand how it works, but it's basically the same thing that we just saw. And it will return also the offset. It will count for us the offset count, return the flags, the message, and the string position. So we can just make this a small loop, and it will run through all the MIDI messages. So let me run this and put just print message type. Let me take this, go down on the code. Okay, now I put the code, the function down here to run it. We're gonna try to see the message types that we have. So let me create another blank MIDI item. Let me run it. So it's without a blank one, we will be just the 11, which is the CC123 at the end. Let me also open the view, run MIDI data. We can see that we have the end here. Let me put a note and run again. And now we have 9, which is note on, 8, which is note off, and 11, which is the CC closing the MIDI item. So this is how you can make a basic loop through through MIDI messages. Now we're gonna see later on how we can manipulate the string itself. Okay, and before we start talking about how we can manipulate the strings, and of course you probably already thought, okay, I will need to use a table and concat the table to a string. But before I show how at least I do this, let's a final thing about MIDI in Reaper, which is called MIDI meta events. So these meta events only exist in MIDI itself. It won't pass for any VST or any instrument. They are just for things that for many things inside the Reaper. For example, the note, there is 4 meta events that I have discovered at least, and they are all size messages. So the binary will be 111111 or FF in hex, and the data bytes will start always with 00001111 or 0F. I think it's always start with this, and after this they will have a text. For example, the note meta message. Let's look at Reaper. What the fuck is this? So here I have a note. You can see here on the raw MIDI data we have our CC123, and we also have the MIDI on and the MIDI off. Okay, so just three MIDI messages. But now if I go, for example, here on the score, and where is this note? Okay, so it is here, and I will put it as, instead of a C sharp, now I will put it as a D flat. Okay, so now you can see Reaper added another message, which is a MIDI meta message. Sorry, it's a MIDI size, but we call it in Reaper meta messages because they only describe things from Reaper itself. In this case, it is saying it's a FF, so it's a size message. 0F is the first data byte, which I don't know for what is for. Oh, I think it should just say, okay, this is the first data byte, and after this we will start the message. So the message is a text, so it always starts with a note, then the channel, which is 0 based, so channel 1 is 0, and 49 is the pitch, which is this D flat, is the note 49. If you go here, you can see 49. So it matches the note, so it knows from which meta messages is from which note tone message. In this case, the note meta messages always comes with 0 offset from the note tone, and it is saying what things it is representing. So here the accidental must be a flat. So this is how you say get or set a note as a flat or as a sharp in Reaper, assessing the meta messages of each note. And if I remove it, the accent, let me see what happens. Oops. Accidental, default, and it removes the meta message. Okay, so there is many things that you can store there on that messages. For example, articulation, put a meta message. And there is another type of meta messages which is always connected to notation, which is things like crescendo, then crescendo. You see here, it added, okay, it's very small. Let me put it bigger. So it is notation, messages, meta messages start with track and then refer what it is doing. In this case, dynamic, crescendo, and the length. And with this, you can manipulate the MIDI notation view. Okay, so these are 2 of the 4 that meta messages that I know Reaper have. So we saw note, the channel pitch, and there is the CCBZ. CCBZ is a little harder to see because it doesn't show here at the raw MIDI data. So it's kind of difficult to study it. But if you go to the famous website, you can see there is documentation about it. So if you search for CCBZ, you see here actually on the get all events, a meta event of type 0F or size message, followed by a CCBZ and 4 more bytes representing the Bezier curve for the previous MIDI event, and the following 4 bytes for the Bezier tension. So this is basically for, let me go here, let me clean this, create another one, and here on the module we'll put 1 cc. Let me view the raw MIDI data, and another one. And if I tension it, we cannot see that it added MIDI meta messages, but we can if we go, for example, in your advanced in the script that I passed to you. Let's use here, for example, the basic looping using iterators. So let me call it basic loop using iterator. It's already calling it. And here, let me print. So let me print the message type. And let me print the text too. So let me actually check if text, then and let me print just a separator here, just this. Okay, now I'll go to Reaper, I will run it. So as you can see, the first thing, okay, it's a little confused because I tried to print the text and the text was with some characters that it probably skipped the new line. but you can see here message type 1, 2, 3, 4, 5. So we have 5 MIDI events happening, and the raw MIDI data only show 3. This is because we have the three CCs here, the 2 we added, and the one ending the CC 1, 2, 3, and in the MIDI item. But we also have these 2 CCBZ meta messages. We can go back to our code. Okay, so you can go to the script that I passed to you. You can use this unpack CCBZ. And let me put if text, then unpack CCBZ, and this should return the base year and the type and the tension, sorry. So this return base year and tension, and we can print the tension, for example. Okay, let me try to run this. Okay, so now we can see it's more organized as well. So message type 11, it's a CC, the first CC here, and it have a CCBZ. It has a CCBZ meta message. So it's good to, in your code, first check if text have that match. So match and put CCPZ space, because text could be anything. So here we are actually checking if it is the meta message, and if it is the meta message, as is in this case, get the tension with the unpack CCBZ and print it. So here the first one is less 0.5, the next one is 0, and let's change it and see it work. Yeah, if I change here is a positive number now, 1. If I go the other way around, it's less 1. So we can change the tension this way. So CCBZ is this. In that document, you can see here, the first byte is for the Bezier type, and the other 4 bytes are for the tension and float. Okay, and we saw track, we saw CCBZ, we saw notes, and the last one, it doesn't have any messages actually. It's just a blank with an offset, and these are will happen only if you have a MIDI message, then another messages that have distances greater than 2/32, which we saw it's like 1 million bars of 4/4. It will add these blank messages to say the right offset, so you can actually have MIDI messages greater than this. You don't have any limit inside Reaper. And this, although this is really great, I won't delve deeper in this because these messages also don't appear on the raw MIDI data window, but you can print it using methods just like this. And okay, we don't gonna go talking much more about meta messages. Now we're gonna talk about a very important thing, that is how you manipulate this MIDI. Okay, we are printing it, but how we change things. And the first example we're gonna see is here, delete CC and add CC notes. This function, let me run it at the end of the code. This function will basically get one CC channel and delete everything, and add a CC message every time there is a note on. So let's see how it does that. So first it defines which CC to delete, in this case is the CC1, and which CC to add, in this case is also the CC1. So we're gonna delete everything on CC1 and add newer CCs there. We could have different values here, but I want to like randomize the channel. And then we're gonna get the MIDI editor, get every take inside this MIDI editor, and for every take we're gonna get the MIDI as a string, and we're gonna create a very important table. In this case I call it new MIDI. You can call everything you want. A blank table, okay? So in here we're gonna store all of our MIDI messages. Okay, so we're gonna store this way. So new MIDI, and then we're gonna have an integer, and this integer will be basically in order, so first message, second message, third message, fourth message, etc. And then we're gonna have, in this integer will equal to a table. In this table we will have offset, which is the offset this message is from the previous message. Offset underline count, which is basically the amount of offset from the start of the item. Message, which will be the mid message as a string. Okay, you could make another structure where you store the mid message as another table, but in this case I will store at a string because most of the mid messages we won't gonna change. For example, in this case we won't gonna change the other CCs, we won't gonna change text, we won't gonna change the notes itself, we won't gonna change. We are just going to change the CCs on one channel. So we don't need to unpack our messages to pack again at the end. We're gonna just store it packet. So message and the flags, which is that byte that says you want it the note selected, you want the note muted, which is the type of curve of each CC. So we're gonna put the flag as packet 2. For unpacking the flags, you can use here, go to the unpack section and look for the unpack flags and the pack flags. So unpack, you put the string of the flags and it says if it's selected, muted, and curve shape. And the pack flags say you put if it's selected, muted, or curved, the curve type, and it will return the string to use. Okay, let me go back to where we were writing. Okay, set, offset count, messages, flags. Let me think if there is something missing. No, so it's just these 4 values we're gonna put inside this new MIDI, inside this table, and this for every MIDI thing. And then at the end we're gonna pass this table, this new MIDI table with all the MIDI information inside it, to this function called packed MIDI table. You are probably wondering why packet? Why not just pack MIDI table? The packet, this part of the function, I call it because the MIDI message and the flags were packed. And you could also create another one which was pack MIDI table, which it needs to pack the message and the flags. But I like to pass the message and the flags already packed, and the reasons I already explained, because we won't need to unpack again many messages that we don't want to even look at it. So pack it because the MIDI is already packed. Here you basically pass the table. It will go through every table there and do a string pack with the I4B C4, basically doing the opposite of unpacking, and then concatenating it in just one string. So this packed MIDI table will return the string that we want. So if we pass to it this new MIDI table with this structure, it will return the string to feed the set all events. So you probably are already understanding how we're gonna manipulate the MIDI. We get the MIDI, And as we get the MIDI, we are going to be putting on this table. And in this table, we can choose, for example, a new offset or put a new MIDI. Okay. And all of these will be packed and setted. Okay, let's continue reading this. So here is the iterator All MIDI. It will return the offset count, flags, message, and string position that we won't gonna use. So I can actually erase this. And first thing, it unpacks the MIDI message. So because in this case we are trying to assess if the message type is a CC, and if it is, we're gonna do some things. So unpacking the MIDI message, unpacking the flags, and here is a variable called was added, because I have in this small thing here, I have 3 places to add or remove things to the MIDI table, the new MIDI table. So here I remove things, here I add, and here I put. I'm gonna in a moment differentiate these things, but I have many places to add this, and if it wasn't added on these 2 first moments, it will be added at the end. Okay, so let's see what is the difference between adding, removing, and putting. So if you're gonna go over the functions on the top, look for the section that says here, MIDI table handling. So MIDI table put is for putting MIDI messages that were in the original MIDI string, and we are not changing the offset value. Okay, so this is really important, because think for a moment here. Let me put this here, my board. So we have, for example, these 3 messages. Okay, so the offset to the first message is X, to the second message is A, and the third message is B. If we would just want to insert these 3 things on our table, we are going, without changing their position, we are going just to use MIDI table put, just put there. Okay, but if we try to change the position of these 2, for example, to here, then we need to make changes on the offset, right? For example, here, to move the message to earlier, we could do, so this would be offset X, this would be A less C, and C is the difference between the original message and the new position. So C equals to original PPQ position, which were this, less the new position. So C is this, is really just this size. And so A equals to, so this offset will be A less C, and this will be B plus C. Okay, so this is a way we could make our table, but it will be really confusing, don't it? Like every time you want to change the position of one message, you're gonna need to also change the position of the next message, because if you put just B here, look at the size of the B, it would be much earlier. The 3 would be like here, and that is not what we want. We want B plus C to compensate it, the less C from here. But there is a easier way, which is adding placeholders. So placeholder is basically an empty MIDI message that Reaper will get it and say, okay, I will delete you. So first we add our first message with the offset X. Second, we add the offset with A less C, and C is the same thing, the original position less the new position. Then we add the placeholder with just the difference, and then we add the 4 with the same amount. So this is really good because we can make a function for this, okay? And it doesn't matter the amount or the orientation that you change the message. For example, here we add the first MIDI message, then we're gonna add the second that was here on this tree, but we actually want to put it really earlier, even before the first one. Could be in any position, it really doesn't matter where. But here the position, the offset will actually be the same thing. A, let's see, A is from 1 to the original position. C is the distance from the original position and the new position, so it is this. This is A less C, this is C, and here it puts the placeholder. You can see here the list, which will be the same thing as the list before. So first is offset X, then offset A less C, then offset C, which is the difference, and this message will be removed, which is the placeholder, and then the offset P, because then we follow along as it was in the originally. And C can also be a negative number, just to show how the amount that you change doesn't matter. So 1 A less C will be this, because C is this amount, and in this case C is a negative number, so A less C, and C being a negative will make A even a bigger number, so in this case goes to here. So C is this difference, and then B. So you can see here the list is exactly the same. The good thing about this is we can make a function to calculate out of this. And you can also use this strategy to add MIDI messages. For example, X offset to the 1, then A offset to the 2, B offset to the 3, and let's say that we wanted to add now some note that was here. We can say, okay, do offset of D, which is D is the position of where you want to add, and the position of the last note, the last message you added. So this will return D, which is this value, and then you add a placeholder, which is the 5 with the negative of the D, just to go back to the position you were before. And this is really great because Reaper will sort things out afterwards, and offsets can be negative then if you need. You can also use this strategy to remove things. For example, the first offset is X, then let's say we want to remove this message. We can put it with an empty message, so the MIDI is just an empty string, and Reaper will remove, but it will keep the offset, and the things after it will be at the same position. If you just deleted these two by not putting on the table, just like, okay, I will not put the table, what would happen is this. The message 3 would get much earlier than it needed. So we need to use placeholders for this. So this is how we manipulate things on our table using placeholders. Or at least how I do it, and I learned it out of these tricks reading some code from Julian Sanders, which is a really great scripter. Probably this strategy is also known to other people, and there is probably more strategies around there that I don't know, but this is how I will teach, because it's how I do it. So I already made functions to do all of these placeholders things. So MIDI table put will just put the things with offset, same position. You can change the message if you want, or the flags if you want, but if you are not changing the offset, you can use MIDI table put because it doesn't need placeholders. MIDI table set is for a message that is already on the original MIDI, but you want to change their position. And this will, just like our example here, just like this or this or this, you have the message 2, yeah, and you want to change their position. And then you just pass the MIDI table you want to add to the new position, the old position, and the old offset that it used to head, and then the mid message and the flags as packed strings and as packed flags, okay? And this will add to you 2 mid messages you can see here. One is the holder, the placeholder, and the other one is the message. You can see the tables here. So this set function used to put a message with different positions. MIDI table remove will just put a blank message at it. It is basically just putting a holder in the place of the original message. And MIDI table add is to add new messages to the table. So it wants the table, the position that you want to add in PPQ, the MIDI message as a packed string, and the flags as a packed string, and it will add the message and the holder. The holder is just to go back to the position it was before, just like our example here. It added the 1, the 2nd, the 3rd, then added the 4th, and then added the placeholder just to go back to this tree, because if it had more messages than this 1, 2, 3, we don't want to change their position, for example. We just want to add the 4th one. Like if there was another offset here that must be the same, with going back and forwards back to the same position, we can put the same value here of the offset. Let's say it was C, I don't know, or epsilon. Okay, so this is why we go back and go forwards. It could also be on the other direction. It really doesn't matter, because it then would go forwards and then it would go backwards to add the placeholder here. Okay, and this arrow actually should be here, right? Or this way, unless the be here, something like this, but it's ugly now. How we can do this? Oh, okay. I think it's better. Let me save this. Okay, so these are the functions that we're gonna use, and let's go back to our example. So delete CC and add notes. Is this one. So we were here seeing, was added. So okay, was added is just to say, okay, if you didn't add in this part of the code, we are going to add now. If just a table put, because the table put is, well, you didn't do anything, I will add it just as it is, with the same offset and the same offset count, the same flags and the same message. And here I am saying, okay, but if the messages that we are looking is 11, the type is 11, which is a control change. So if it is a control change, and the value 1, the first data byte, which tell which control channel it is equal. If it is if it is equal to the CC I want to delete, we're gonna MIDI table remove, which will just put that placeholder that we saw, which would be this example here. It is just putting the placeholder there, just to hold everything in the same position. So it's put in this placeholder and say, okay, this message was added. And then it won't be added here. And then it could also be a note on, and it needs to be a type 9 without being with the velocity equal to 0. This is data byte 2, which tells the velocity. It can't be 0. And inside it, we are getting a random value between 0 and 127, and making a MIDI message. This MIDI message is a CC with the value of 1. Sorry, it's a CC with the channel 1 at the channel 1. The pack MIDI messages is 1 based, the channel. And we are using the CC to add is this variable, which are telling which CC channel which CC we are adding to. So it's the first data byte is it will be the number 1. And random is the value of it, which is this number that we are getting between 0 and 127. So this is basically a CC message of on channel 1, and in this case on the 1, which would be a CC mod wheel, right? This is a mod wheel message. Then we are passing some flags, which is, if it is the MIDI message selected, we say false. Is the message muted, we say false. And which type of curve we want. In this case, 1 is equal to a linear. You can see here, linear. And we are adding to the table. Okay, but we are not in say was added. Why we are not saying was added? Because here I am doing this when I see note on messages. So I am doing this whenever past the note on message, I am adding a MIDI CC 11. So I am adding it. It wasn't even at the table. And now that I added this CC, I want to add the note that we triggered this code. Okay, so let's see what this does. So if I create some notes here, and this is at the first channel. If I run this, if I run again, what it does is, if it find CC1, it will delete it, and if it finds find a message that is the note on, it will add a CC at a random position. At a random value. So okay, quite cool code. Let me put more things. Yeah, I put a lot of things. And as you can see, this is quite fast too. So okay, this is the first example. Now let's see the second example that gonna just randomize the position of each note on. Okay, now let's try to see the last thing for finishing this video. So this will be in the file that I passed you, the last function, sorry, not the last, previews of it, randomize notes get set all API. Let's call it at the end. Basically what this function will do is randomize the position of the notes and print in how much time it did that. So it's I put a really small value, and this is a big timeline. Let me put some zoom here. Okay, so if I run it, you can see the notes are randomly changing their position. Let me put more notes. Okay. Now if I select everything and run the function, it randomizes the position. Let me go back a lot. Okay, and now let's try to analyze the function and trying to understand it. So first thing, this start time is just for printing the how much time it took to run it. So here I just use it here at the end. So start time. Oh, sorry, this is not the function I want. Is this one on top is much bigger. So here's start also with the start time. It's just to get when it started running, and then it just use it to print how much time it took to run the function. And okay, before it, random range is a variable of the amount of randomness you want. So 50 milliseconds. In this case, we could put bigger values, so it would randomize a much more. Let me save the thing. So now it's randomizing by a much bigger value. Go back to here, and then the MIDI editor, then iterating every take that is open on the MIDI editor, getting all event for each take, get out events from it and get as a string, create the new MIDI table with the sorry, there's missing set count if or flex is a string with this structure that we already saw to use the handling functions, and also creating another table which is called offset note. This table is really important because there is two things that we also need to change with the logic is this: when you find a note on the loop, we're gonna change their position randomness, but we also need to change the note off by the same amount. So we are storing in a table how much each note changed. Also, we are storing the original position because the new position, because the meta events we need to change together with the note to the newer position. So if we had like 3 events, the note, the meta event, and the note off, we needed to run it earlier. We need to also change the note meta event to this new position and replace the position of the note off to be earlier, the same amount. Now, so we are saving here on the offset notes table channel, which is the channel of the notes that we are changing, the pitch of the notes we are changing, and we are inside this making also a table with n events, and for each integer is a table also with the change is how much in PPQ that we change it, and new PPQ position is the new position in PPQ. So the change will be used to move the note off by the same amount, and the new PPQ position is to set the meta event at the same position of the note. Okay, so we need to have this as a table. We pitch and then integers as a table because in Hyper we have to account for nodes that are like this, one node that is inside another node. This is actually invalid by MIDI protocol, but in Reaper for some reason it's valid, and this shouldn't happen. You can also turn an option on to never do that. So if you try to do this, it cuts the MIDI. But I, in my scripts, try to acknowledge it. I don't know if if it is the best thing to do, because it shouldn't be allowed actually. But anyway, I do this by putting more tables here in the integer. So to demonstrate the structure really fast, so in this case that we have two notes overlapped on the note 60, let me put here, on the channel 1, we would have offset notes, and then the channel 1, then the note 60, that would be a table, and on the first note you would do something like table insert, and in this table, which is this one, we would insert another table, which would be called which would have the change with the offset, how much it changed, like less like 160, and new pp key position would equal to the new position, I don't know, something like this. And then when this note on reached, it would add another thing on this table, which is this one here. For example, it changed this by this amount, and the new position is, I don't know, this, I don't know. Just an example of how is this structure. So okay, let's see the first iteration. We won't gonna use this. So same thing, offset counts, flags, and messages. First thing, it will be unpacking the message. And then it was added for the same thing. If you go minimize this, you'll see the same code. If not was added, put on the table. And here, this if condition have two else if. So the first is if is selected and it is a note on, then it will get a random value between range and, well, this is between the less half. For example, if the range is 60 milliseconds, the range would be between less 25 to 25. That's why I'm reducing by the half, and then making it in seconds, because this is the value in milliseconds. So then I am getting this note position in seconds. So the note that is filtering here, that is we are iterating, we are getting in seconds from the using this function get project time from ppq position. We pass the ppq position of the note, it returns it in seconds. Then we add the position to the random value we got, that is already in seconds. And then we get again the position in ppq. So math floor get a ppq position from time. Then we pass this function, and remember that the new ppq position need to be rounded to an integer. It can't be a float or double. It needs to be an integer, because we can't have like 2.5 ppq. We need to have integers. If you try to pass a not rounded number, it will error at some point. So always remember to round the number. I use this function math floor, so it's always the going down, but I added 0.5, so it is always to the closest value. So if it is closest to the lower, it will go lower. If it is closest to the higher, it will go higher. If you don't know this trick already, let me draw here really fast. If you have a number between, I don't know, 0 and 1, and like example, a number here, like 0.8, it should be rounded to 1, right? If you use just math floor, it would be rounded to 0, but if you added 0.5 to it, you would get 1.3, and it would with the math floor go to 1. And if you had a number like 0.3, add 0.5, it would equal to 0.8, and it would go to 0. Okay, so we always add 0.5 to round the number. Then I am clamping this value at 0 because we couldn't have a negative number, try to set a negative number, and this new PPQ position until here could be 0. Now I am making it to 0, and then I am calculating how much the note changed on the final PPQ position. So the new PPQ position less the original PPQ position, which is offset count, which is returned here on the iteration function. Then I'm inserting in the new MIDI table. Okay, so I am MIDI table set. I am using this function because I am changing the position. Remember, you use, if you aren't changing the position, you use the put. If you change, use the set. If you want to remove, remove, and then add a new message, the add. Okay, let me go back to that place I was here. So here we are setting to a new position. We are saying, oh, we added this message, so it won't run here. And then we are saving how much it changed and the new PPQ position on the offset notes table. Okay, this is just the thing I explained about the structure of this table. And this table will be really useful now that we need to change the note of position. So here, if we select it, and it's a note of type, or is a note on with 0 velocity, which equals to a note of, we are going to check, and I use this function table check values. You can try to study it why. I won't go deeper on here. If this address is, if this table exists, and if it exists, we are checking if the offset notes, if there is something here. Okay, so this first checks if this exists. I couldn't just pass this, like, I couldn't do this. Oops. If you know already a little more about tables, you know why I couldn't do this, because this could bring an error and break the script. Because if I try to access this, which will always be a table, this not always can be a table. And so this would return new, because there wasn't a key here. So this would return new, and then the code would try, okay, new val1. This returns error. And that's why I use this function, because this never returns a new. It will be trying to access it, and if not, it will just return false. But okay, it returned true. So, and it will check if we know that this exists. Now we will check if there is more than one value here. This is basically this table. This table here with I 1, 2, 3, 4, etc. We are checking the amount of it is bigger than 0. And if it is bigger than 0, and by that we mean there is some note on that passed, we are getting the new PPQ position, and here, which is the offset count, which is the current note and position plus the change, and we are removing it from the table because we don't need it anymore. The note already passed, we can remove it. And then we set to the table because we are changing the position, and we say was added. And finally, we are messing with the meta events. So if it is a system message and the channel is 16 and it starts with the note space, which is how meta messages of notes start, then we're gonna get the channel and the pitch by getting the text and matching. Here we'll return channel and this pattern will return pitch. Then I am just making channel equals to 2-number channel plus 1, because this here is a string still, so these two things are strings. And now they are numbers and channel is 1 based. And then I am checking the values just like this, if there is something, note on that passed there, and if there is something on this table. And if there is, get the new position, MIDI table set, and set the this message, which is the meta message, to the new position. And we say was added, so it don't pass by here. And this is how this function works. So for changing a note position, you also need to change the note off if you want to change by the same amount. So you need to consider the note off and pass information for it. And you also need to consider the meta messages. Don't go and just change the note position without considering the meta message, because you, let's say if you are messing, for example, a user that uses a lot of notation, you are going to remove information from him, and you probably don't want to do that, and neither the user wants. And then you pack the table and set all events. So yeah, this is an example on how it works. So if you run it, it randomizes.